Okay, so we have an arbitrary truth table where we now have the associated K-map that we've decided what the mapping is, right? A, B, C, D. Is there any confusion in filling this out? Yeah.
So is this F with the don't cares on it? Is that the continuation?
Yes, this is the first 8. This is the second 8. So we're going to go there, right? Because 4 variables means I need 16. And then once I establish the direction that the pattern is going, as long as I've drawn it intelligently, it will just go column, 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 and we just fill it out really quick. Yeah. So don't cares or whatever is more convenient for you. That's the wonderful thing about the don't cares is I can pretend like they are whatever I want. So if it happens that not circling an X is helpful, don't. If circling an X, meaning including an X in your implicant, if it's helpful, do it. If not, you don't need to include it in your implicants. In fact, you don't need it for coverage, right? That's the idea, is coverage means I've circled all of my ones, I've included all my ones, or zeros, right? If I'm doing a product of sums, which we'll do both of, because it turns out the product of sums is probably pretty easy on this one as well. Although I suspect that the sum of products is simpler, just because of large groupings, right? Like I can go look and see that this 0, if I'm going to use the zeros as implicants, which is how I design a product of sum circuit, that's on its own, which means it's going to be a fairly complex term because it's going to have all A, B, C, and D variables in it. Whereas like these ones, you guys want to take this and take a moment to start circling your implicants on your own, and then I'll come back, because I don't think everyone has done that. So I'll give you a minute to start circling your implicants, keeping in mind things like coverage. Make sure you get all of your ones. If it helps, I think there's going to be 4 implicants with a minimum of 4 min terms in each implicant. Yes.
Okay, I'm just a little confused with your extension on the last row, because you have 3 X's in a row and just 2 X's and then 0.
Oh, did I do an extra X? That's okay. So I went X, 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 0. Because these 2 are flipped, remember? This is the 1, 1 term, and this is the 1, 0. So this row and that row are flopped so that we can maintain logic adjacency.
And then these 2 columns also.
Yes, exactly. The columns have also been flipped. So specifically going down, right? This is min term 0, 1, 2, 3, 4, 5, and down. Corresponds to 0, 1, 2, 3. so that I can keep logically adjacent, right? Because 3 is logically adjacent to 2 because of this 1, 1. Only this variable changes, therefore logically adjacent, therefore it will simplify. 3 is not logically adjacent to 4, right? Because 3 of those variables change. However, it is logically adjacent to 1 because only the b variable changes. That's why I flip them. So if you want in your notes in preparation for like an exam when you're inevitably going to see a K-map, if you wanted, you could just write a K-map and write where the midterms go. As long as you understand that this A has to be that A in order for this ordering to work. That's how I decided to do it this direction. I could just as easily put the A here and it would have made just as much sense. It's not wrong to do it in any order. I could do like A, C, D, B. It would work out, but it would just be, I'd be bouncing around a lot on this K-map and it would be hard. It would take me longer to fill out. Yeah.
So a good rule of thumb being if you're going from truth table to K-map, that your left twomost will go on the top and your right twomost will go on the bottom.
Yes, if you want to just memorize this or mark it down, it will work every time. That's what it's perfectly fine. Any other questions before I start circling some implicants? Great. So what do we do to start? Yeah, big circles, right? We want to look for big circles. Sometimes we're going to realize that we don't need the biggest circle because it's just going to become redundant. I don't think that's the case here, but let's find out, right? The big circle is fairly obvious. We need to stick to the rule of 2 to the n, which means 1, 2, 4, 8, not 6, and they must be squares or rectangles, right? No weird 90-degree turns inside. So what we do is we see this big block of 8. That's nice because we know that's going to result in a term that drops a fair chunk of those variables, right? Because it's anything that changes is going to go away. And remember that just has a relationship to what happens when you write the midterms, right? That's just the logic adjacency. Now we have to kind of make the decision, well, what's our next kind of big? And there's a couple of 4s that we could do, right? These 2 are hanging out on their own. But specifically this 1, I need to get that 1. But this is a 0, that's a 0. However, there is a cube there. That's nice. That whole cube was there specifically just to get that 1. You might be tempted to circle only that 1 because why would I draw a bigger implicant? Why would we? Why would we draw a bigger implicant? It simplifies the term, exactly. So what's the next color? Green. I got a green. This one, he's kind of on his own. There's 2 good answers for this one. What are they? Yeah, we could wrap a square around, right? This one, that one. Well, this one, that don't care. This one, that don't care, right? That would be perfectly fine. What's the other one, anyone? Exactly, the column. I have a tendency to prefer the columns if I can, because it means that these are my go-aways and these are my stays, and it's just really easy and quick for me to identify what doesn't change if it's a column. I like columns more than squares. It's just preference, it doesn't matter. They will result in different circuits, but they will both be equally minimal. Okay, now I've got one more 1, right? This guy. What do I do? The 4 corners. You guys are good at this. 1, 2, 3, 4. Now I go and ask the question, is this orange one necessary? It is, right? Because it's got a couple of 1s that aren't included in any of the other implicants. If we ended up in a situation where that wasn't true for some reason, if you had a bunch of overlap and you realize that you have this big implicant that's not adding anything to it, it's okay to go back and erase. But I do need this one to complete coverage. Now we just have to write the terms, right? Or yeah, the terms that come out as a result of this. And it's just a question of what doesn't change, and we say F. And by the way, the notation on the K-map is usually just right above it. We write the variable that we're interested in solving, because we have to have unique K-maps for every output, right? How would we imagine making a different output off of one K-map? It doesn't make sense, right? So each time we have an output, we want a unique K-map. All right, so then what we say is F is what? Well, let's go ahead. I'm going to try and keep this color coordinated, actually. And let's start with the green one. The green one's easy, right? We just ask what doesn't change, and as I already pointed out, it's that column of ones, which is CD. C and D specifically, right? And there are no not bars on that because it's ones in that column. The orange one, we like the orange one. If 4 results in a term with 2 variables, we would suspect that 8 is going to result in a term with only 1 variable. So there's only going to be 1 variable left when I go and look at this. And we can say that B, right? B isn't changing. C and D obviously are, because it's spanning the whole distance across the top. So C and D are going to change. A changes, B doesn't. And in that pair of rows, B is 0, therefore bar, or tilde, I guess now. So I've got green, let's do red. So red, we're looking at what doesn't change. Across the top, it's 0, 1, 1, 1. So C isn't changing across that top. That's useful. So or C, and it is a 1, so we can leave it. And then we have to look at the vertical part, because anytime it's a square, right, we're going to get 1 on each side of that, basically, is what's going to happen. And it is the A that doesn't change. And it is also a 1. Last but not least, the most complicated one, right? The 4 corners. This one's just kind of annoying to visualize. It's not any different, but it is obnoxious. So let's look across the top again, which is going from 0, 0 to 1, 0, which leaves the C isn't changing, and it's a 0. So not C. And then the vertical part is going from the top 0, 0 to 1, 0, and it is the A that isn't changing. And that's not. Yes.
At that point, could you simplify the AC and the A and A not A and not C?
These two, what would they simplify to? They don't. Here's why, right? And this is one, I've pointed this out a couple of times. It is very important. It is very common to make this mistake, especially on the exams when you're crunched for time, which is just to say A and B knotted is not the same as not A and not B. Those aren't the same. So you could pretend like A and C is a term we'd call alpha, let's say, right? Where alpha is just A and C. And what you're trying to imagine is this is alpha or not alpha, but it's not. It is not the same. In fact, however, you're not wrong. This feeling that like it should simplify is actually a fairly reasonable feeling to have because it is so approximate. This does simplify if I'm not constrained to one kind of gate. If I had a pile of any kind of gates, that does simplify. Does anyone recognize what that is? Truth tables are our friends. AC 0, 0, 0, 1, 1, 0, 1, 1, right? This just describes all possible input combinations to this A and C. And I say that it is true if I have 1, 1, or 0, 0. Yes. So if we look at the invert of this, and I'm going to call this alpha, right? I called it alpha. This is not alpha. Not alpha is 0, 1, 1, 0. That is an XOR, exclusive OR, right? It is true if and only if one of the inputs is true. But if both, it is not true. That makes that XNOR. So this does simplify in a way to a single gate that is an XNOR. However, there's no real good way to convert from XNOR to NAND or NORs. So we don't do it. This is the most simple canonical form is what they're called, right? If we were to write this expression, right, we have canonical forms for this expression for F, which is one of them. One of the ways we can write it is truth table. We can also describe it using a mathematic expression, which is just to say, we know those min terms, and those min terms are ordered from top to bottom, and those min terms are the sum of the min terms, little lowercase, I'm sorry, M0, comma, M1, comma, M2, dot, 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 right? I just write down the M index for every one, skipping the zeros. Then the don't cares, I say plus the don't cares. The don't cares are just a lowercase d. And then I would write, well, it's 7, 8, 9, and 15. That's the canonical form. So if I give you that equation, that means it's that truth table, which makes that K-map, which builds this circuit. Right, it's all related. We're just using math to design circuits. Okay. Let's move on to the new material. This is not erasing very well. There we go. I'll leave that for a bit. Okay. So what we're going to do today is, well, the first half. We've so far, when I've done the truth tables, right, I've just told you the pattern. You can generate any truth table just by going 0, 1, 0, 1, 0, 0, 1, 1, then 4 zeros, then 8 zeros, and so on, right? But we want to expand that to number representation, right? We actually want to understand how binary numbers work, how hexadecimal numbers work, right? Hex is coming up. So let's start. Binary numbers are really easy, right? So in decimal, we write 137 like so, which is the same thing as saying 100 plus 30 plus 7, right? Each of these columns, this is a column, each of these columns has a weight associated with it. Now, it may not be clear in all cases. Well, actually, I'll come back to that. So binary is the same. It's just that this decimal has 10 different options that each column can be. We denote that by saying it is base 10. We don't do that in day-to-day because we assume that whoever you are talking into the world is assuming a base 10 numbering system. Now, that's actually a fairly good assumption as long as you're not dealing with small indigenous populations in very remote areas. I don't know this for certain, but I am pretty sure that I have had an anthropology class once upon a time that says there are cultures that are indigenous to areas in remote locations that have non-base 10 numbering systems, which is fairly interesting. I don't know, go Google it, let me know. We use base 10. What that means is there are 10 options. Binary only has 2 choices, right? On or off, 0 or 1. So we would write a number like 101 base 2. Just like decimal, there may be a situation where I don't need to tell you that it's base 2, right? So I can just leave off that little 2 because it's understood that in context, it's a binary number. That's fine. It's going to do the same thing, except for each column isn't 0 to 9, it's 0 to 1. And each of those columns is going to have a weight associated with it. In this, each column has a weight of 10 times the previous column. Therefore, in base 2, it is 2 times the previous column. So if I draw a nice big block, now I can make what we would call an 8-bit binary number, right? I have 8 blocks, 8 bits. Each block is a bit. In decimal, each column is a digit. Decimal, or sorry, decimal, digit, binary is, sorry, my name just blanked out like really bad, right? Anyways, decimal has digits. We don't call them digits in here because they're bits. There we go. Had to start from the beginning. Sometimes I get confused. All right. This has a weight of 2 to the 0. Just like this is a weight of 10 to the 0. What is 10 to the 0? 1. So it's just the number here times 10 to the 0, 7. The next column is 10 to the 1, which is 10. So you take 3 times 10 is 30. Same thing, 2 to the 0, 2 to the 1, 2, 3, 4, 5, 6, 7. Once you have this understanding, converting from binary to decimal or decimal to binary is just a game of addition, right? I can just add the weights. So let's say I have that number. Well, all I have to do is go and identify what are my weights. Well, we've already established that this is 1. If I have a 1 there, it is equal to 1. If I have 1 here, 2, 4, 8, 16, 32, 64, 128. Let's add, right? That's all this is. If I ask you the question, you're gonna get a question like this on an exam, that I'm gonna give you a binary number, and I'm going to ask you to convert this number to a decimal number. That's one of the possible questions. When you do that, I will probably also specify something like and show your work, because I generally don't really care what resources you have. If you want to bring a calculator to check your work, go for it. But you have to understand this because I'm going to say show your work. And drawing a picture of a calculator isn't going to count for that. Don't worry, I was a student too, and I was lazier than any of you were. All right, so that's just 128. That's what that 1 means. Plus 32, plus 16, plus, well, not 8, right? Because that's the 0. That means I don't add the 8. Another way, if you want to be tedious, like the book is, I could say that it is 0 times 8. And I could write it out for every single one. The 0 times 8 is 0, which means I can just ignore it. And then say add 4 plus 1. Note that if you ever have a 1 here, that means your number is odd. So you can always quickly check your work. If you've done a conversion and you end up with an even number, but there's a 1 here, you did it wrong, right? You added something weird. Because there are no other odd numbers that are going to exist, right? Because if you're doubling something, you can't double into an odd number. We add that up, and well, 128 plus 32 is 160, plus 16 plus 4 plus 1, which is 160 plus 16 is 176, 180, 181, I think.
Yeah, you got it.
Cool. Yeah, I don't know. I'm a little rusty in the mental math, but there we go. That's all the conversion is. I think I posted the homework already. If not, I've written it. I just have to post it if I haven't already posted it. It's just going to have you do some number conversions. It's not rocket science yet, right? We're obviously going to get more complicated because we always do. We're engineers. We have to make it more complicated. And it turns out 8-bit numbers are not very big, right? They're not really, they can only store 128 plus 64 plus 32 plus 16, right? All of that added together. That's how many numbers it can store plus 1, because it can be 0. So it goes from 0 to 255. There are lots of situations that we probably want more than 255 numbers available to us, right? So what we have to do is extend that out, we have more bits. (128) times 2 is 256. Times 2 is 512. Times 2 is 1024. Times 2 is 2048. That is now a 12-bit binary number, right? However, there's a problem. In that right now, as written, I don't have the option of making a negative number. So the question becomes, how do I make a negative number in binary? Yeah, put a minus sign. The problem is, where do we store that minus sign, right? That's the problem with the computer, is that on a whiteboard, I can have sloppy handwriting and put the minus sign wherever I want and everything is okay. And as long as it doesn't look too much like a tilde, you guys will understand what I'm trying to say. However, I don't have that luxury in a computer. That computer has to have some way of knowing what is that value. Well, the easiest way is, let's say we have a 4-bit binary number. And I say, well, I need to know if it's negative. And I just say that this is my plus or minus column. And now this number, 100, right, which is 1, 2, 4. So this number is 4. Well, now it's negative 4.
Does that mean an 8-bit number is really just 7 bits?
It becomes 7 bits. So we lose some information when we want to, well, we don't really lose that much information, and we'll see why, right? Because what is the maximum value of this? Well, the maximum value is 0 plus 4 plus 2 plus 1. So we have a range of 7, 4, 6, 7 to negative 7. Yay, right? Unfortunately, there's a problem. This isn't perfect. This works really well if you want to keep things simple and you want your life to be easy. However, engineers like things to be optimal, right? We like to optimize things. We're obsessed with it because we're like, well, if we can save even the tiniest bit of energy or space or memory or whatever it happens to be, we've done a good thing. So what we say is, what is the difference between this number and that number? Yeah, negative 0 is the same thing. So I've now thrown away a value. I've lost values in here. Now, in this case, it's actually fairly significant, right? Because I have 2 to the 4 options, or 4 bits. That's how many choices I have. That means I have thrown away 1/16 of all of my options. Just lost it. So some engineer, smarter than I am probably, came along and came up with this really obnoxious thing that we call 2's complement, which is a different way of encoding binary numbers. So encoding is just a way that we say of representing, number representation. How do we represent a number, right? So right now, if I say, I want you to write -7 for me, without being more specific, you guys could write -7 in decimal or -7 in binary, and you would be correct, right? They're the same thing. It's the same concept. We just drew it a different way. It would just be like, if we happen to know Roman numerals, we could write -7. Right? I'm sure we all could puzzle out what 7 is in Roman numerals, and I don't know if they use a negative sign or some other way to represent it. I'm not a historian, but we've come up with probably a couple more ways to represent -7, right? We'd probably like a negative sign and do like, there we go, -7, right? You guys know what that means. Anyways, all I'm saying is number representation is a concept that you're very familiar with, but you haven't heard the word. So don't be worried when we talk about the way we represent numbers. It's just a different way to write it. We just have to communicate that there is a difference, right? That's 6. If you have bad handwriting, you might be tempted, like me, to write it like that, VI. And we have to know that there is a difference between this horribly written number 6 and the character in the recent League of Legends or video game and television show, right? Bye. I know you guys might not play that. I'm not a huge nerd. Anyways, we want to represent numbers. We have to know how it's represented. So if I'm asking you for binary numbers, I mean binary. This means unsigned. There's a kind of implied idea that if I ask you for binary, it's an unsigned binary number, meaning there's no sign. This is a signed binary number. Unsigned, signed. Let's add another one that we're going to call 2's complement. 2's complement is designed, well, in part to address the issue of optimization. We don't want to lose data. We don't want to waste storage. So what do they do? Let's start with 4. 4 is easy to handle. Well, what they did is they started with the same thing: 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, but they just said this is now negative. Negative 2 to the 3. So if I put 0, 1, 1, 1, I end up with 7. 4 plus 2 plus 1, 7. If I do this, well, this has a weight of 2 to the 3, which is what? 8, right? So 2 to the 3, so I'll just write this up. So 1, 2, 4, 8, right? 2 to the 4, there could be 16 possible values, but we're just changing how they're distributed. Instead of throwing away 1/16 of them, we're going to say, well, this number is equal to negative 8. Oh, not 8. Off by a column. Negative 8. So my range, okay, this word is going to come up a lot in electrical engineering. Range is not how far the weapon in Halo fires and hits things, right? The range is basically just the highest value minus, or the highest value to the lowest value. So we're going 7 to negative 8. That's our range. So it turns out we have one more negative number than we do positive number in 2's complement. There's no real difference between this representation and that represent the signed representation, except for we just have to keep straight that not only is it negative, it is negative with a weight. So if we have a number, well, this one is still weighted at negative 8. But the other ones are still weighted at positive numbers. So it is now negative 8 plus 2 plus 1, negative 8, negative 6, negative 5. Okay, makes sense? And take practice, right? We're gonna have to go do some homework on it, blah, 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 figure out get it ingrained in our memories, and then promptly forget it as soon as you take the final for this class. I'm joking, this will stick with you because it's so simple, right? This is an easy, nice break from all the complicated stuff that we've been doing. However, as with all things engineering, there's still a problem. What if I want to communicate data to you and it is a 32-bit number? That gets really annoying really fast, right? That is a lot of ones and zeros. Well, I can still do it in decimal and know that there is an equivalent binary number. It turns out that there is another way of representing numbers that we call hex, hexadecimal, which is basically like, what is hex? Does anyone know what that prefix means? Yeah, it implies 6, right? Hex is like a hexagon. And so all it's really doing, well, is saying that it still has decimal in it, right? So we're going 0, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to stop at 7 and flip over because I know some of you guys can't see that very well. 7, 8, 9, 10. Well, hexadecimal is a number with a base of 16. It wants 16 different options. There, I did it, right? I have 15 options or 16 options. Well, no, because it really means it wants 16 options in every single column. And in order to do that, I ran out of columns, right? Or sorry, I had to add an additional column in order to make this representation. So what they do is starting at 10, because 10 is where the problem arises. And they write A. A is now 10. Unsurprisingly, they're going to go in alphabetical order. So 5 is still 5, but E is now 14. And the number is perfectly valid. A7 is totally fine. That is actually a valid number. And to make things more complicated, this is not obviously hex, right? This could easily be decimal. So I would need to specify either in the question that I gave you or in the context, some way to let you know that this is hex, because it's not clear. This is pretty obvious, right? If it's a number and it has an A in it, unless I've taught you other things that use A's, it's safe to assume that that is hex. But this one, I probably want to say 16. But what is 16 in decimal? Well, the number, it's going to be bigger than 1, because 1 in hex is 1. Right? And in decimal, we write 16. But in order to get 16, what comes after F if I'm counting up? Okay, but I've limited myself to this limited number of characters.
1, 0?
Yeah, I go to 10. The next number after F is 10. So this is 16 in decimal. So this column is D for decimal, and this column is H for hex. 16, 10. Because the same thing happens as in decimal. When I go from 9 to 10, 9 is my last decimal number. I ran out, I need a new column. We start at the beginning 1, and then I start counting. So I am now 10. In order to get 16, there are 6 more of these, right? So 16 plus 6 is 22. So that's 22. Pretty sure. I could be wrong. That's 22 base 10. Yes.
Is it because, just like we were thinking back to like this binary, you're gonna have one or never mind. I was thinking of it.
All right. Let me know if it comes back to you. This next step might actually help, because it is actually fairly difficult for most people to convert from a hex to decimal. It's actually really weird because they're so close to each other that it gets confusing, right? It's very easy to get confused when you're doing like 16 to 22 because 16 looks like a decimal number. So what we like to do, or at least what I like to do, the way I teach it, is if I ask you to convert from a hex number into a decimal number, let's take a pit stop and do it in binary. Because binary is easy. And it turns out that converting hex to binary is trivial because there are 16 options. Why does 16 sound familiar? 2 to the 4. That means 4 bits. It means it takes 4 bits to represent each hexadecimal digit. Yes.
So I was thinking, so with 16, you could basically break that up to 1 times 16 raised to the first plus 1 times 16 raised to the 0. Which
yes.
Is 1.
Yes, you absolutely can do. All he's saying is if I have this, it'd be 1 times the base, which is 16, but we're in the tens place, right? The book formalizes that. There's express equations. If it helps you, if you're that math oriented, just go read the book. It actually kind of formalizes exactly what you just said. So good catch. I'm going to stick to kind of the conversion thoughts because it ends up being a little bit easier, and no one's going to do it that way in real life. But if it helps you, if you're that math minded, I'm not that mathematically minded. I'm just going to go and say, if I have the number C7, well, I can come over here and build something like a truth table. It's not really a truth table. What it's going to be is what we call a lookup table. Okay, so what a lookup table is I take an input, decimal, and I go look up, what is my output? Well, it turns out it's kind of hard to do that in just hex because of the way that our brains work. At least it is for me. I don't know, maybe you're smarter than I am. And I'm just going to go 0, 0, 0. Oh, it's not a 6. Sorry, my zeros degrade the more of them I draw. Right, so I've just assigned decimal values, sorry, binary values to each of my first 8 hex characters. Jump down here, do the same thing. Well, now it's easy. Now I have these binary values associated with my hex values. And now I just go over my conversion that I've asked you to do. I want you to convert C7 into decimal. I go look up. What is C? C is 1100. See why it's a lookup table? I just looked it up. I just looked up what C is. Guess what? Lookup tables are really common. They're a very common engineering term that we will use a lot of in 3610 in digital systems, actually. When I say 7, what is 7? Well, 7 is easy, right? We know 7 from binary, or we can go look it up. 0, 1, 1, 1, right? 4 plus 2 plus 1. Well, guess what we're going to do? We're just going to start adding those up. 4, 2, 1. That makes that 8, 16, 32, 64, 128. Conversion done. Barring whatever mental math errors I make. So if I ask you to do a 16-bit number, as long as I don't put anything past G in the alphabet, we should be well within our ability, right? 7A, C, 4. Take a moment, convert that number to decimal. Let's double that. 400 and I think that's enough of the values, right? That do those doubles, right? Turns out timesing by 2 is really hard after 6 o'clock. Right, and then I just go find the ones and I start adding those weights to them. So like this, I'll erase this for a second. So this 2048 is tied to this one. Where's my other colors? This one is that value, this one is that value, and this one is that value. So it is what? 16,404 plus 8,192 plus 4,096 plus 2048 plus 512 plus and so on. There you go. Right. I mean, I assume that you guys can do this. If you happen to take the exam and you don't have a calculator and you write this up and you write out the equation that is this plus that plus this plus that, and then say, I don't have a calculator and move on, guess what? I'm probably going to give you all the points anyways, because I'm not going to judge you for doing things that my brain doesn't want to do anyways. Right? As long as this is the concept that I'm looking for, that you understand how to do this conversion. And all I want to point out with these is that you can go the other way. If I give you a hex number, and I say this is this is a binary number, and I want you to convert it into hexadecimal. Well, it turns out there's a step that we have to do first, because we're going to go 0, 1, 0, 1 is 5. I walk over, I say this is 5. 1, 1 doesn't fit hex. Guess what? Just like in decimal, hexadecimal doesn't care if you write a whole bunch of zeros in front of it. Well, I don't want a whole bunch of zeros. I want just enough zeros to represent some multiple of 4. And now I have 0, 0, 1, 1, and I say 3. That number is 35 in hexadecimal. If you want to do it in binary or in regular decimal, right, in human numbers, then we would just multiply by the weights and we're done. That's all number conversion is. That's all number representation is. The only other thing that I want to point out, this won't be on the exam. I don't like doing it, but it is helpful to be aware. Let's say I have that number, right? Because I can have 137.5. I'm allowed a decimal point. This is not a decimal point because we're not in decimal. This is a radix point. It's just less than 1. It marks the separation between things that are more than 1 and things that are less than 1.
So this is active? Yes.
It does. It works the same way in base 2. So what we do is we say, well, we know that this is 8, right? 4, 2, 1. What does that make that?
1, 2. Reverse. Go that way.
Right? I'm just dividing my 2 as I go along. Yeah. Right. I'm not going to ask you to do this, but I do want you to be aware that we can represent numbers less than 1 using decimal or hex or any of those. I am not going to ask you to do that. We have things that I'd rather spend my time on reinforcing, but I do want you to be aware that this happens, because what you end up with is something called float. So what happens in a computer, right, is I have some number of digits or bits allocated to my number storage. And I can't magically create more, but sometimes I want to be able to do things like multiply 137.5 times by 10,400. One of those has a decimal, one of those doesn't. And all float does is it allows the decimal point to float around. Now that gets really complicated, and you'll learn more about that if you take, I think, embedded systems or computer architecture. You get much more detailed into that. For now, we're not here to overwhelm you. Just be aware that it exists. The number representations you need to be aware of are unsigned binary, signed binary, 2's complement, hexadecimal.
Signed binary, that's just where your first one decides that's 0.
Correct, yes. Okay, so pretend that you guys are in 1st grade or so, and you've now, in kindergarten, you learned all of what your numbers are. What's the next step? We add them together. So let's move into how do we add binary numbers together? Okay, well, how do we add binary numbers together? It's pretty simple, which is to say, if I want to add the number 1, 0, 1, is this green okay for you in the back? Okay, just want to check. 1, 0, 1 plus 1, 1, 1. We add those together. Well, we could do this, hopefully, maybe, but I'm not going to assume that you know how to do things I haven't taught you, because that's me, right? So let's talk about it. Well, if I want to add the number 7 plus 4, I get a 1 in this spot because it makes 11, right? We can do this mentally. Maybe it is past 6. And then we get a, what we call a carry, right? A carry value just sends out. Well, we have a whole bunch of different options when we're adding decimal numbers. What's nice about binary It's really only like 4 options for that first column. Right? Well, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 0. With a carry.
Okay. So it's 10.
Yeah, 10. Yes, yes. 1 plus 1 is 10, obviously. Unless you're some famous basketball star that thinks like 2 times 2 is, I don't remember, a disaster of a math tweet. So now we have a problem, right, where we have this carry. And so now I have more options because the second column can have what we call a carry in, meaning a number comes from the previous column and makes us do something with it. That's annoying. It's not too bad. We can then say, well, my only options are 1 plus 0 plus 0 is still the same thing. And I'm going to simplify and say that it doesn't matter where in this column the 1 is, it's the same number. So this represents several what would be columns of my table, but 1. Similarly, I can have 2 1s without a carry. And it makes a carry. Or, right, it's the same thing. It doesn't matter if I have a carry or there. It's the same number. It's just addition, right? 7 plus 4 is the same as 4 plus 7. So that leaves my only remaining thing, 1 plus 1 plus 1. In other words, 1 plus 1 with a carry in. Meaning the last column had a carry out. So like, hey, what is 1 plus 1 plus 1? Well, we know that's 3. So then I just go add what is 3 in binary? 1 1. You now know everything there is to know about binary addition in an analog world. In a digital, there's a problem a little bit, which we'll get to here. But let's do this, right? We can now add this number really easy. Well, 1 plus 1 is 10. Yes, absolutely. 1 plus 1 is 10. Is 2. 1 plus 1 is still 2. 1 plus 1 plus 1 is 3. So there's a carry. In a digital system, as I've said before, there's a finite amount of memory. I need a place to put these numbers in order for it to remember. For us, that can be anywhere on this whiteboard. For a computer, it needs an allocation. So if there's not one, we call this overflow. If I have only allocated 3 bits to my numbers, I add them together, it comes out OVF, overflow. Yeah. Let's do one more example, just to say that I did more than one example for you guys. In fact, I'm going to make you do it, right? So that you don't like see me doing, oh, that makes sense, and then you promptly forget. So please add these numbers for me together. Yeah, add those numbers. Yeah.
Really how it overflow is like, let's say, you know, even though we had those 2 numbers, let's say we had a 4-bit number.
Yeah, correct. So if I was adding 4-bit numbers, it's no longer overflow. Or you don't have to really know this yet, but there are some computer architectures that actually have special little bits of memory designed to store the overflow, so that you can go back and use it. Overflow. Right? Get this? Okay. There's a thing that you can do as well, which you could just go look at these two numbers if you weren't sure. You want to check yourself, and you go, this is 1 plus 4. This would be 8, so 16, 21 plus 1 plus 2 is 3, plus 8 is 11, plus 16 is 27. 21 plus 27 should hopefully be 48. And then that's saying there's 1, 2, 4, 8, 16, 32. 32 plus 16 is 48. We can make sure that we're not crazy. Yes.
So if, let's say you're adding like, so you got like an overflow plus 1 plus 1 plus 1, what do you do in that case when you have 4 1s you're adding together?
Well, in this case, we're not going to really have the possibility of having 4 plus 1. So 1, 1, 1, 1, 1, 1. Right? That's the kind of situation you're worried about.
Or like one more, like there's, so you'd have 4 1s in a column that you're adding.
Oh, so you're worried about
Yeah, what do you do in that case?
that? Well, it turns out it's the same thing that we would do in any other situation, but it gets complicated and annoying, right? Because 1 plus 1 plus 1 is 3. Which we're fine, we can do 3. And now we have 1 plus 1 plus 1 plus 1, which is 4, which is 0 with a carry. And now I have 2 plus 1 plus 1 plus 1. So 2, 3, 4, 5. Now I just write the decimal or the binary for 5, and I'm good to go. I'm not going to have you do that. I don't have to worry about it. When you take digital systems from me, I will teach you how to multiply these numbers, which is really fun, actually. And I'll have you design a multiplier, not on breadboard, don't worry, that'd be horrifying. But the multiplier is actually really fascinating because it's a real serious problem, actually. Multiplication is an issue. And I'm going to avoid getting stuck on that tangent because I will absolutely do it, but we don't have time today, unfortunately. Great, perfect. Any questions on addition? So next comes subtraction. I'm not going to cover subtraction yet. It's in the same chapter of this book. By the way, I have received an email. There are now more books in the bookstore. You should be able to go pick them all up. So I'm going to stop posting the chapters. Let me know if they run out again. I'll reach out and talk to them if that's the issue. I don't think there is. There's supposed to be 15 of them, and I only counted 12 students between my 2 sections that didn't have them yet. So there should be enough books now, which is awesome because that means I can now say we can go ahead and have open note, open book exams, right? Because everyone's going to have a book in person. Our exams will be open note, open book. Don't rely on your book. The other warning that I want to say is make sure you do the homework. I know that you can like go online and find the answers to some of them, but the problem is when you have the answers and you do the problem looking at the answers, what your brain does is it convinces you that you know it because the patterns feel familiar, right? It's like singing along to your favorite song versus being able to sing the entirety of the song without any music playing. They're not the same thing. So don't practice the wrong way, right? I want you to all succeed. I don't have any way of forcing you to do that. I'm not going to look over your shoulder. I'm not running like cheating scanning on your homework because guess what? All of you are going to have the same answer, hopefully. But do yourself a favor and do the homework and then look up the answer. That's totally fine, right? If you've done it and then you look at the answer to see if you did it right, that's okay. Following along step by step will not help you. Okay, so I've got to switch topics here for a moment. And this is a very large topic switch, so give me just a minute while I pull up my laptop and regather my thoughts because I want to make sure that I don't come off as insane, pretty much is what I want to say. I can torture you if you guys want. This is actually probably a really good idea. K-maps are a really important idea. Have you guys started the K-map homework yet? Yeah, I didn't think so. But it's due like Monday or Tuesday, something, right? Get started on it. Okay. 2 steps that I want you to do. First thing that I want you to do is write the first the first 6, I'm going to put a 6 here, the first 6 rows of this truth table based on that K-map. And then I want you to find the product of sums expression for this K-map. Any questions? Yes, product of sums, which means your form, right, is going to look like yes. I missed a 0. How many of you have all of your implicants? Not quite all. All right. I won't quite write the answer up yet. Yeah.
So just for your like sums, whenever you have a one, that's right.
Yes.
Like on this far right column, on the top, that would be like a, you know, the top side would be a D, not
This one.
or a, yeah, a C, not D, or C or not D.
So this one's D and that's C. So we're going to do C, D. The C has a 0, so it's good. The D has a 1, so it is not D. But we have to flip the gates. So we add the or, add the parentheses, and prepare our next term. Yeah, that's the question. All right. Unfortunately, I got to move this a little bit. I know some of you aren't quite done yet. It's just practice, right? It doesn't really matter. I've said it before. I'll say it again. In engineering, it matters very little how smart you are. It matters a whole lot how hard you work and how much practice you do. Some people are going to have an easier time at this, right? That's just the way things kind of work. But don't be discouraged if you're slow, because we're all bad at something. I wasn't always very good at this, to be honest, when I was an undergrad. So all it's saying, I've color coded them, right, with these little asterisks. If you have any questions on these or anything that I did wrong, right? So like this one's the easy one to explain, the black one, which is the A and B don't change, but the C and D do because it spans the whole width, meaning C and D both change, so it's not going to be part of the term. I look at A as a 0, B as a 1, which means that A doesn't have a bar and B does, right? So the product of sums means that form, which means circle the zeros. We can find the relationship, right? We could also do this with ones just fine. The nice thing is that when I design it this way, what I end up with is, well, the output is gate is AND gates. So I say this is AND, and it has 1, 2, 3, 4 OR gates associated with it. Two inputs, two inputs, two inputs, three inputs. I'm not going to write them all, right? There's inverters associated with each of those each has term. But the nice thing is now I ask the question, please convert this to NOR gates. What do I do? Well, the input of the first gate, I add bubbles to every single channel. If I skip one, then I have a problem, right? And really there's double bubbles here. In order for it to stay the same equation, I have to invert the invert. To do that, I just go put a bubble at the output of each of the ORs. Everything is NOR logic. We've designed a NOR logic. That's why you would choose product of sums, one of the reasons. Great. So now we're going to move on, unless we have questions. Yeah.
You could also go on the second column on the left. You also go up and down, right?
Yes. So this one I could loop around over the top. Is that what you're asking?
Yeah.
Yeah. So this 0 and that 0 would be perfectly fine to do. Once again, you would have, right, it would just be this term that is the 3 would be one variable different, but otherwise the same. And it'd be the same complexity, and the same function ultimately, just a little bit different. Yeah.
So that's not the only right answer then?
Correct. There are multiple correct answers using K-maps.
Is there an advantage to just going up because then you just put 2 zeros in, and then you're not adding a not there?
Not really, because we already have that 0 covered, so I don't have any concerns about it. Yeah. If it wasn't already covered and I had to have an extra implicant because it wasn't, then I would want to add that one in. Do you have a question in the back?
Talking about the C and not D.
The C or not D?
Yeah.
So the C or not D is this one.
Why you did the not.
The D, because the D is this one. And ones are, in product of sums, are not what we're looking for. So we put nots on the ones, we don't put nots on the zeros in product of sums. In sum of products, when we're circling the ones are what we're looking for, so we get the ones, right? The way to think about, another way of thinking about this is product of sums is basically generating active low logic, right? It's looking for the active low signals. The zeros are on for that situation. Basically all it's building. Okay. Good. Okay. Now, I'm going to show an example, actually. This is what we're building up to, and I'm glad you asked this question, which is there a reason why we might choose one over the other, basically? And I'm going to build a much simple, are there any questions on this one? The stage? Because, right, all I did is the reverse, is I just looked up the other way. If I toggled these around, it's perfectly allowable. It would be confusing, but you could do that and puzzle it back out. I don't think I'll do that to you. The worst case, they'll be alphabetical, just the A would be here instead or something. And if it helps, if you end up in that situation and you're not sure, you just write, this one is D, this one is C. They both have knots for sum of products, or by the invert of that if it's product of sums. Again, don't forget to use the gray code, right, when you're writing out the columns, meaning you flip the third and fourth column. Right, back to 3-variable K-map. We're going to keep this one simple for this example. We go and look at it and say, right, there's two pretty obvious implicants on this one, which is there and there. And then when we evaluate that, I'm going to still just stick to F. I'm going to look at what doesn't change. I'm going to do sum of products on this one because I circled the ones, right? That's what that means. And I say, okay, well, in the first case, in either case, C is going to be there. And it's just in this case, C is a 0. So because C is 0 and then A doesn't change, it's going to be not A and it's not C. Or, well, this one C is 1 and B doesn't change and B is a 1. So it's or ECE. Right. Well, we go and design our circuit. Has an OR output gate because it's sum of products, 2 AND gates. And then I go ahead and I'm going to use the inverters this time because it's important. And I'm going to say A goes through an inverter into one of those AND gates. And C is going to turn out that it makes more sense to draw C in the middle, where one of them goes through an inverter and one of them doesn't, and then B. Right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Perfect. Okay. So now we're going to talk about a fun issue, which is called hazards, which correlates to timing. So I've talked about how these gates take time to react. They're not ideal, right? When I put an input in, it takes some amount of time for the output to change. So we've kind of treated them as ideal situations. We've done a homework where we drew a couple of timing diagrams that were ideal, right? So if I have like an ideal situation where I have inputs into an AND gate, which are A and B, and A does this, and B does this, then the output we're calling AND, right? Well, 0, 0, it starts at 0. It stays 0 because 1 and 0 is not on. 0 and 1 is not on. But here at this point, I have a 1 and 1. So I look down, straight down. I have little dots on these board. I'm cheating, so it is actually lined up. It goes to 1, but as soon as they both go to 0, it falls away and it stops being 1. Right? This is timing diagrams. Well, we're going to use this tool a lot. Timing diagrams are really important. And generally, I haven't introduced these in this class until later, until after you've learned VHDL, after you've learned to program hardware, because this is actually how we analyze circuits when we've designed them in software, right? When we've programmed them, which is hard, when we've described them in hardware using code. We're actually going to look at a whole bunch of timing diagrams. So I want to introduce them now as opposed to later, so that makes sense. And in order to do this right, we have to talk about delays. So each of these gates is going to have some amount of delay. One of the things that is a bit of an issue that we're not going to really deal with too much in this class, which is that each of the gates types have their own delay potentially, right? Because an inverter has different properties than a NAND gate, say, which has different properties than a 2-input NAND gate has a different property, different amount of input capacitance is really what it is, but it has different properties than a 3-input NAND gate, which is different than a 4-input NAND gate. So each type of gate can be different. For this class, and this is your first digital logic class, right? We're going to just kind of assume that all gates have the same delay. This is actually not that bad of an approximation for most purposes. So we're going to have some delay that we're just going to call D, and we're going to evaluate what happens to this circuit as a result of these non-ideal timing properties. Well, it turns out the K-maps are really good at this for us, because what the K-maps say, what the K-maps tell us when we design this, is they actually have a way of communicating that there is what we call a timing hazard, which means we might run into a problem. And we know this by looking at the K-map, and if we find any situation where there are adjacent ones that don't share an implicant. So two adjacent implicants that don't overlap at all, like so, will cause what's called a timing hazard. Now, I'm going to show you what it is. That's why I drew up this thing. But I want you to understand first that these K-maps are wonderful at telling us you might have a problem and you need to think about, does it matter in your case? In a circuit, what you want to know is there an input that has different number of gates between it and the output? Meaning, does it take the circuit longer to react to that input in two different paths, different times? So here we can look and say that C is our problem, right? Because C, in one path to the output, goes through 1, 2, 3 gates, and in the other path, 1, 2 gates. This is what we call a static hazard. What the static hazard means is it's supposed to stay 1, or it's supposed to stay 0, and it doesn't. So the first thing that we have to do is what's called prime the circuit. What this means is set up all of the inputs that aren't hazards in a way that the one that is will change the output of the circuit. What do I mean by that? Well, if I have an AND gate, with inputs X and Y, well, if I set X to 0, so that means I'm only interested in those top two. Does it matter what Y is doing? This is AND, right? Yeah, it's always 0. It cannot react to a change in Y because it's not primed, right? If you're military or if you played various video games, I don't know where else you run into it, right? To prime something just means to make it ready, right? If you've painted, right, you have primer, you put it on the wall first so that the paint will stick better. Primer is designed to stick to things well. However, paint, maybe not, but paint sticks to primer really well. That means just get it ready. That's all prime means. Get the circuit ready, prime it. Well, we can tell already in an AND gate, priming means to set the inputs that we're not interested in to 1 so that it can react. In an OR gate, it's the opposite, right? In an OR gate, we just set the inputs so that it is 0. Because if it's a 1, if one input in an OR gate is 1, the output is always 1. It can't react. So we go and look at this circuit. We have AND gates. That means in order for C, our hazard, which is a hazard because of this, right? Has one extra gate in one of its paths. It can't be a hazard if it only has one path. A and B, no hazard. Okay, so that means A has to get set to something that allows this gate to change. What is that? Well, I need a 1 at the input to the gate, which means A has to be 0. B can just be 1. There's no inverter, I just set it to 1. Now my gates are primed. In a sum of product or product of some situation, I only have to worry about my inputs, right? Because the intermediate signals, these connecting signals, depend on what I'm doing with my inputs. They're ready. So now what is this circuit doing in this static situation? It's just sitting there, I've set it there, it's there for a long time. Well, I have C. Let's pretend that C is 1. And there's a reason. I'll explain why in a minute. Well, let's say that I set C to 1, which makes this 0 and this 1. 1 and 1 is 1, right? Now we're coming back to the circuit analysis thing that we talked about weeks ago. Everything's kind of tying in together. 1 and 0 is 0. So that means this is an OR gate. There is a 1 here. There's going to be a 1 at F. What happens if I put a 0 on C? Well, that means I have a 0 at this input and a 1 at that output. Well, that means there's a 1 here and a 0 here. And guess what? F is still 1. So if we're primed, I can change C and nothing happens if I don't account for time. Now let's see what I mean. Let's say that I have I don't think I actually need that many vertical bars. Well, I want to be primed, so that means I'm setting A to 0, B to 1. I don't have to draw those up here, right? They're constant, but it may help for the beginning. So A, B, I said A is 0 on forever. B is 1 on forever. Okay, that's my situation. Then I ask myself, well, if I call this one X, this one Y, well, I need a C, I need an X, I need a Y. In fact, it may be helpful to you to add in like the not A on this, or just draw it as not A, right? I think I'm going to do that for the moment. I'm going to call that not A so that I can, because that's the input to this gate, and that's what I care about. And since it's not changing, I can kind of take that shortcut and not A is 1. And then C is going to start at 0. And I'm going to change it to 1 here right at this green bar. And then here at this green bar, I'm actually going to change it to 0. Again, I need to go one more, and you'll see why in a minute. Okay. So what happens to X? Well, X is not A, right? Sorry. Not A and not C. That is this. So where do I have not A and not C? That's all this timing diagram is asking for X. Well, in the beginning, I have not A, because that's 1, right? I've drawn this as not A. You could see how you could just draw this as 0 and just know that it's the same thing. But now I can treat this as a 1, so I have not A and not C. C is a 0, so it's true, right? Well, it's going to stay until something happens. I'm going to call these important points, right? Transition points, something along those lines. Something happens. C changed. I've already said A and B aren't going to change. They're fixed. I've changed C. Well, let's say that each of these green bars represent one gate delay. One delta. There's another way of saying that. Delta being a change. I can also call it like delta D, Y, delta T. There's lots of things. I'm just going to call it a delta. Anyway, it's just a gate delay, one gate delay. I've said that I'm going to treat for the purpose of this class, I'll make gate delays are the same. This is a bit of an oversimplification, but the idea will translate. Well, that means X sees the change in C. When? When does it see the change in C? Well, X has to wait 1, 2 gate delays before it changes, right? through the inverter, through the AND gate. Okay, so 2 gate delays later, it's going to drop down to 0. Because X is no longer true, right? X stops being true because C is 1. It's supposed to be 0 to make X true. It's not. It drops to 0. Well, guess what? It changes here. Now I have to wait 1, 2 more gate delays before it changes again. 1, 2 gate delays. Now it can change. That makes sense to everyone? Okay. Let's look at Y. Well, Y starts false, right? Y is not true in the beginning because Y is B and C. B is true, but C is not. So not true until C changes. But guess what? It's not 2 gate delays later, right? Or it is 1 gate delay later because it only sees this gate. There's no inverter. So after 1 gate delay, it gets to change. So C changes here, this green line, 1 gate delay later, it becomes true. It stays true until C changes again. After 1 gate delay, it stops being true. Well, I called this F. My output is F. F no longer cares what's happening to the inputs, right? It looks strictly at X and Y. And it is true if X or Y is true. And it is 1 gate delay after that happens, is all. So after X or Y changes with 1 gate delay, what's the color I haven't used? Blue. So it cares when X or Y changes. So here, here, and here are where my X and Y change. Yes.
So is it 1 gate delay because the F itself is the gate that X and Y are going through?
Well, F is the output signal. But it is the F gate. Yeah. So we could call this like U0, U1, U2 to give them labels. Make sense? So it is U2's gate delay that has to wait for X and Y. Good question. Okay. So F, well, F is true if X or Y, right? That's all F is saying. F is equal to X or Y. And X is that, Y is that. I can substitute just like in algebra. But I don't need to. I've abstracted away these inputs. I'm going to look at my timing diagram and ignore A, B, and C. They're useless. It's clutter. As long as I've done X and Y right, I'm good to go. Okay. Now I go and look. F is true because X is true. And it can't change until something happens. Until there's an interesting point, there's a transition point. It's stuck. When it does change, it waits a whole gate delay. But what's interesting here is this became true, and this is already true. So it's still true. Everything's fine. Now this is dropped to 0. This is still true. Everything's fine. Well, now this is an interesting point. It drops to 0. Okay, well, what happens at 0? Well, 1 gate delay later, which is way over here, it drops to false. Because at this moment in time, I'm running out of colors. Both of our inputs are 0. And then after 1 gate delay, oh, it came back true here. So 1 gate delay after this guy, it comes back true, and we're back to normal. But we know that we've primed the circuit, which means that regardless of what A, B, and C are doing, well, specifically C, right? Because A and B are fixed. that regardless of what C is doing, it is supposed to always be 1. That's what I showed here, right? It's not. That is a static hazard, which is it's supposed to stay 1, static, unchanging, doesn't move. It's supposed to stay 1, and it doesn't. So if this circuit is very precise in its timing, and I don't take care of that, now I have a problem. Now I might throw out a 0 when I'm not supposed to. So let's pretend that this circuit is feeding an active low reset. Reset being something that says go back to your default position, right? Go back to the beginning. So if it's like a counter, I've mentioned counters before, 0, 1, 2, 3, the reset comes, go back to 0. Well, let's say this is looking for some sort of input and C is just kind of toggling around, but it's supposed to stay, it's supposed to stay 1. We just accidentally reset. We accidentally reset the counter. So, how do we fix it? What did I say? What was my initial condition that I knew that there was going to be a hazard in this circuit?
That you didn't have the 2 adjacent circles.
Yes. How would you say it?
Well, you said that we have 2 ones that are adjacent, but they don't share an
Implicant.
Implicative? What's it?
Implicant.
Implicant.
Yeah.
When you said that, my first thought was, can't you just be like a little bit less space efficient to save time and give them an implicant together?
Yes, exactly. You both said the same thing. You're both correct. It is because I have 2 implicants, they have adjacent ones, and they don't share. I add an implicant. There are now no longer any adjacent implicants, rather adjacent ones with non-overlapping implicants. I have added kind of a dummy implicant here, but what that gate does, well, this one changes here, so it is A, B, the A is knotted, right? Is that true? And it's going to add an extra path here from A and B. And it turns out right, symbolic connection, it's okay. It turns out that this not A, B gate will hold it true as C changes. It no longer depends on that C. It addresses the one condition. It's no longer optimized for size, but it's optimized for speed, safety, right? I've traded circuit complexity or circuit size for robustness is usually the term you'll hear in engineering. The circuit is now more robust. It doesn't have this hidden weakness where I might slip up and have a 0. Make sense? Well, it turns out that if I design a circuit using sum of products, I will end up with what is called a static 1 hazard, meaning it may have an issue when it's supposed to state 1 and doesn't. If I make it a product of sums, if I circuit the zeros, I may end up in a situation where I'm supposed to say 0 and I don't. Make sense? That's static hazards. That's timing and delays. Those are gate delays. So we can arbitrarily design circuits, choose circuits, right? This is what happens when I've designed the circuit, right? I know what it's supposed to do. I found the issue. I've utilized my K-map. in order to make sure I don't run into problems at high speed. This may or may not actually be a problem depending on your design. That's why you're going through all of this painful engineering education, is to be able to make intelligent decisions when it comes to these trade-offs. Yes.
I have a question. That priming thing confused me. Did you just do that for simplicity's sake? So
No. The priming thing I did is because I knew that C was going to be my problem circuit.
because it was the one that.
Yes.
Okay.
And so I set up all of the other gates that C was plugged into so that C could change the output.
So in a real circuit, if you were testing for the error, that's what you do. You prime it. But like if you're just using it, you wouldn't have to prime it.
Correct. If we're just using the circuit, we don't have to prime it. Priming is for discovering where the errors are.
Okay.
Yes.
So if you had like, let's say you have 4 inputs and 2 of them, you have a hazard on, would you just like prime everything but that and then figure it out and then do the same thing with the other one?
Yes. You would do them separately. You would prime for, so if you had A, B, C, and D, and B and C were the ones with potential hazards, you would prime for C and then prime for B, and you could discover them. So basically what I'm going to do is I'm going to give you an exam question that reads something like, given this circuit, use the following timing diagram to identify the static hazard, right? And I might specify, like you might start from a K-map, like use this K-map, find the ones, build the circuit. I generally don't do that. I hate grading them for one, which saves you guys a lot of pain. So generally what I'll do is the question is going to be kind of A, B, C, and D, but part A will be like, here's a K-map, solve it. Okay, here's a different solved K-map, use this to convert it to NOR gates. Here's a different one, identify the timing issue, right? I usually decouple them on exams because if you mess up on part A and you do B, C, and D right, I want to give you all the points for those because you clearly understand the other parts. However, grading that is a nightmare. So generally they're going to be decoupled is what we call them. Let's see if I can't make up a interesting circuit. So this is an OR gate, right? So this OR gate is going to be true if this or that is true. So we're going to start, take a moment, draw the circuit, and find an expression for F. Oh, good question. Sorry. I wanted to do a 4 input and I just forgot to do the D. Thank you. That doesn't work out, does it? You see why this circuit doesn't quite work? Yeah. I've kind of trivialized it on accident. So let's see. It's fine, right? This is fine practice for the circuit analysis, which is still going to be good questions. I can trivialize this real quick by replacing this AND gate with just an inverter. Now this is not C or D, and F becomes something that is a little bit less mundane, which is A and B and C, or not C or D. Right? That's better. That isn't just going to simplify away, and we're good to go. So now C is going to have two paths. I'll wait while you guys redraw so I don't overly lose you. Sorry, people are still drawing the circuit. That's why I'm just standing here. As this is a really important idea, really important concept. It helps understand the circuits. All right, so what we're going to do is I'm just going to start naming some signals, right? It kind of helps us to give names to things. I'm going to call this X. And this one I'll call Y, and this one I'll call Z. I may or may not end up using Y, right? Because Y is just the opposite of C or D. And so I can, as long as I draw Y or Z, I'm probably okay. As long as I understand the number of gate delays. And now I could ask the question quickly, what signal likely has a hazard? C. Now, it turns out, right, this isn't a product of sum or a sum of products, so it may not be obvious if it actually is or not. So let's find out, right? I could ask the question, does this circuit have a static 1 hazard? Would be a good one, right? That tells you that you should, if I ask static 1 hazard, that tells you should prime the circuit so that the output starts at 1, and then change whatever one you think might be problematic and see, right? Let's find out, does this circuit have a static 1 hazard? Or I could ask, does it have a static 0 hazard? Would you prime it to go to 0 and find out? Right, that's kind of what we're looking for. So let's find out, does this circuit have a static 1 hazard? Step 1, prime our circuits. Well, A and B, what should they be? 1, yes, absolutely, right? Because if they're not 1, C can't do anything to that path. So A's 1, B's 1. Then we say, okay, well now C here, what is D?
0.
0. Because if D is not 0, then we have a problem because C won't change that path. Then we say, if C is 1, that means that ABC will be, I'm going to change colors. A and B and C will be true. And if C is 1, Y is 1, that's 0. Which means F is true because X is true, but Z is not. If I flip it and C is 0, then that's 0, but this is 1. So now we're starting to look like, okay, there's probably going to be a hazard here, right? Because there's a situation where C has 2 different paths, and one of those makes it 1 when the other is 0, and when I flip it, it changes. If they were both 1 and both 0 in the same situation, there's probably no hazard, right? Because I don't really care. If it's doubling up the 1s and doubling up the 0s, same input, no hazard. This, however, is a hazard because of this inverter. right? Because C's path here is 1, 2, 3 gates. C's path here is 1, 2 gates. Different number of gates, probably going to be a static hazard. Last time we kind of figured out that, well, let's see. Let's see if we can think about it, right? Last time it happened when C went from 1 to 0 was the issue. Should we start there? Should we go start C with 1? And we've gone through the full thing, so I'm going to simplify, and I'm just going to write C with the understanding that A is 1, B is 1, and D is 0. On an exam, I'm probably going to make you draw them, but it's really easy to draw 1, 0 across, right? And you don't have to draw all these lines yourself because I will provide these diagrams with enough lines for you. I don't like drawing that many lines, and it's going to take a lot of time. So let's go ahead and call that C, X, Y, X, Y, Z, F. Great. Now C, I said I want to start it at 1. I only need to wait for 1 gate delay just to establish that it's there. It's really helpful to draw that initial starting condition and then go change it. If I want to set this up for future, just in case I want to know if it's going to happen on the other direction going 0 to 1, say, what I'm going to do is I need to wait down at 0 long enough that I don't have these weird overlapping effects. You can do it, but it's very confusing. So I just recommend going and looking at your delay path. In this case, it's 3, right? My longest delay path is 3. I walk over here. I wait 3 gate delays, and then I can change again. If I don't wait 3 gate delays, I can get weird overlapping effects on my timing diagram, and it gets very, very difficult in order to interpret the results. Take a moment to draw out a timing diagram and fill in for X, Y, and Z. Right, Z should be trivial once you have X, because Z is just, sorry, Y, because Z is just Y with 1 extra delay, or the inverse of Y with an extra delay. you don't mind, put your pencils down when you're done so I can kind of monitor, because I want everybody to get a chance to do this, and then I'll run through, because this is a important concept.
Let me ask you, are we to assume that like F will start off at 0?
What are we primed for? If A is 1, B is 1, C is 1, and D is 0, what is F?
F would be
1. Yeah. So we primed for 1 because I said let's test for a static 1 hazard, which says let's see if it's.
so the first signal going through C would be 1.
Yeah.
Like it
But-
are-
But we don't have to know, right, other than the priming, which is what happens, which I designed the circuit, right, in order to make sure that it was 1 with C being that potential hazard. I can prime for 0 and test it that way, static 0 tests. There is a bit of an issue like this one. You can kind of work through it and see that there's no possible way to have a static 0 issue. However, if those inputs were NAND and NOR, we would probably end up with a static 0 and not have a static 1 possibility. Because you could think about, right, a fair question would be, how do you prime for a NAND and NOR gate? Or how do you prime for an XOR gate? That's kind of a hard one. Okay, it looks like we're good, right? Sweet. So I did look it up while we were doing this because I wanted to go back and figure it out. It turns out there is a wonderful example of a culture that does not have a base 10 numbering system, which is the Mesopotamians who use a base 60 numbering system and resulted in 60 minutes in an hour. Pretty cool.
Yeah, it's true.
So I'm not just making stuff up. I do have a memory, at least for something. All right. Let's go ahead and just start solving this, right? We know that F is going to start at 1 because we designed, but let's go ahead and look at what is X. Based on A, B being 1 and D being 0, and we want to draw X because I can't really worry about any further things until I have the intermediate signals, right? So what is X? Well, X is A and B and C. And A and B are both 1, so it is just asking the question, is C true? C is true, X is true, right? It drops, but it takes a gate delay before that changes. And again, it rises, but it takes a delay before X follows. Let's go look at Y. Y is true if C or D is true, but D is never true, right? We set it up so D is never true. I'm only asking, is C true? Well, it's going to follow C then with 1 gate delay. C changes, wait to gate changes. Sees the change, wait to get delay, Y changes. Okay, that's easy. Z then, we can stop worrying about the input signals and worrying strictly about the intermediate signals. Y, or rather Z only depends on Y, so we just look at Y and nothing else. And we just say Z is not that with one gate delay. So Z then follows C with 2 gate delays, right? If you were really confident, you could skip the Y, because Y and Z are very easy to determine. If you're not comfortable, don't. Doesn't take you a lot of time. It's worth a little bit of extra time to make sure you don't make a mistake. Then we go ask the question, F. What is F doing? Well, F starts as 1 because, well, F is the equation A and B and C, or C or not C or D, which is another way of saying X or Z, right? It would be very hard to evaluate this looking back all the way at the inputs, but looking at just X or Z, is X or Z true, is fairly easy. X or Z. X or Z. Well, X is true to start, and I always assume that it's whatever this is basically forever leading up to it, right? And that's kind of what this would imply. We then go ahead and say, well, X changes here to 0, and oh, look, there's a 0 on Z. So with 1 gate delay, we drop to 0 because we have a 0, 0 here. And then finally, we go back to 1 here, but it takes a gate delay from here to there before it changes. We go on. Well, here, we already set to 1 on, we set to 1 here on X, but we're already 1 on Z. So we're fine. That's not going to have a static 1 hazard. It just stays 1. We found our static 1 hazard. Okay, yeah.
Are the way like NANDs and NORs built, would they, I guess we kind of made up that everything has the same delay per gate.
Yeah.
But like, is that kind of how that works? Could you,
Kind
like,
of.
replace, could you put the inverter into that OR and have a NOR, and then there's like 1 less gate delay so that they're the same?
Right? This is a X. This is a inverter. We can also have what does this do? Right, we just do this by parts. What happens if A and B are both 0? Well, if A is 0, this guy is a switch that closes because the bubble means do the opposite, means turn on. So if A is 0 and B is 0, then these both close and the output is power. If either of A or B is 1, it can't be 1. And then we can go say, well, the pull down network, remember, pulls to 0 and it's parallel, and the pull up is series, which means they're never going to be activated at the same time. This is a traditional architecture that makes it safe that we don't light anything on fire. So then we just go write the truth table, right? We have an A, we have a B, 0, 0, 0, 1, 1, 0, 1, 1. I keep trying to count in gray code. And we don't know what this is yet, right? and we say, well, if they're both 0, 0, 0, I get a 1. Otherwise, I'm getting a 0. NOR. Right? Because the opposite of that is OR. So if you're not quite sure on something, invert it and see what the inverted is and see if that's familiar. Right? Because it is harder to see NOR than it is OR. Find it, just flip it and find out what the opposite of you're looking for. So then the question was that brought us here. This is a good review, actually. I'm glad you brought it up. Is the delays, are they roughly the same? Well, no, because do you remember what I said caused the delay? You don't have to know. It turns out this is extraneous information that you'll learn more about. But do we remember? Yeah, why is it?
Didn't you say the electricity has to physically push something?
Well, that was more the conceptual idea. But what it is it has to charge it up. It's capacitance. It takes a while to charge up the circuit in order to work. So then when the first electrons flow through and run into it, it's like a big bucket. And not until that bucket fills up does it change over. So it turns out that each one of our transistors has its own bucket. And so I have to fill up more buckets in the NOR gate than I do in the inverter. So the NOR gates are slower. I have to fill up more buckets. Yeah.
So this is what a buffer would come into, like would you use a buffer with the time gates to kind of?
So no, actually, we don't try and do that because there's even more complicated, and this is like an upper division / master's class elective that we go talk about this. There's this thing that we call PVT, which is crap. I forgot the V. Process, temperature. I'll figure it out. Anyways, basically what it says is when we make our semiconductors, they come out on discs. You should go YouTube a video of making semiconductors. It's really fascinating. Anyways, the parts that are in the middle are different than the parts that are on the outside because they're not uniform manufacturing. And so all of our NAND or NOR gates aren't even the same speed. Everything varies. We have some amount of reliability and we have a bunch of math and prediction and models that tells us how good they are, and we can simulate it. We can put all of this information into our simulators and find out if we design. But in general, we just don't do this. We use our K-maps and add a couple of extra implicants, and now it doesn't matter how fast they are. As far as the hazards go, there's still a limit, right? What our maximum speed limit is kind of determined by the capacitance. But good circuit design will put us in a situation that those maximum speeds can be achieved safely. Yes. Voltage. Thank you. Yeah. So, right, the input gates are going to have a little bit varying voltage on them, and it's going to have some issues around that, basically.
That's kind of what your PVT does when you're analyzing the circuit.
You would eventually if you became a circuit designer at this level, right? It turns out most of you won't. Most of you are just going to, a ton of you will end up using VHDL to go write code, and then you'll have simulations that will tell you if your circuit is going to work or not, basically. And we'll start to touch on that throughout this class and more in 3610 digital systems. Again, you guys have to know this architecture, right? Evaluating what they are. You don't have to remember PVT. This is just kind of right, extraneous information that's kind of interesting, and it's where you're going and it matters. Just not yet. The main takeaways from today are understand priming, right? That's a big one. Be able to draw timing diagrams with delays. I do my best to try and give you guys gate delay vertical bars. If I forget, just draw in roughly equally spaced vertical bars and say, this is one gate delay. Thinking back, right, the first half of the lecture, number conversion, we want to be able to convert between binary, hex, and decimal. And binary includes signed, unsigned, and two's complement. Right, that's what we learned today. That's our takeaways. I think it's 7:30 now. Yep, it's 7:30. We're gonna wrap up a little bit early. I'll hang out and answer questions if you guys want, because the class goes till 8. As I mentioned before, I have a daytime class that I try and keep this in sync with, and those are 2-hour and 15-minute sections. So sometimes you guys get a little bit longer lecture. I don't do it to torture you. I do it because I think this is fascinating and I want you guys to be good engineers. But tonight you are free to go home and take a nap, or better, go do the homework for this class. If you were confused on the dice light bulb question, I will go ahead and do one of those a little bit right now as part of a review. Yeah.
The delay between is added.
That's what I was.
Or would it be very?
Oh, it turns out it would be much longer actually, because a NOR gate is this, and OR gate is this with an inverter attached on the end. Okay, so that this has to charge up, and then this has to charge up, and then the inverter has to charge up.
So this is much slower than just a NOR.
Yes.
Okay. I just wanted to see like how that timing would change.
Yes. No, good question.
Yeah, so.
I got a question.
Yeah.
So why do we, I don't like why, this changes just the one delay here.
Yeah.
Then why is it 2 here instead of just a?
Because I'm holding C there for 3 counts. So this is just that delayed by 1.
And we're holding C there for 3 counts for why?
So that because if I drop this 0 and then 1, then this is going to go 0 and then 1, and then this is going to go 0 and 1, and then this is going to go 1 and then 0, and it gets really difficult to spot this happening. So basically what kind of happens is this window gets shrunk down to nothing if we don't give it enough cushion potentially. It just gets harder to drop. That's really the answer.
For the homework, homework 4, I see.
Yeah.
So this draw that came out, it was 2005, but for this guy, I'm supposed to do where you split it.
The Morgans, yes.
The Morgans. Okay, just want to make sure.
Okay, so you're starting at 1 because you're inputting C at 1, right?
Yeah, because I want C to be 1. I
Yeah.
want this to be true. Yeah.
So then you're dropping.
Yep.
Because of the inverter, correct?
I am dropping because I chose to, because that's my test. I want to know, because C has 2 paths, I want to know that when I change C from 1 to 0, do I have a static hazard?
Okay. And you're, like you just said before, you're doing the 3 time zones so then you can calculate.
So that it's easy to see. Yeah. Basically, weight a number of gate delays equal to the maximum delay path, and you'll be good.
Oh, all right.
Dice. Anyone else for not dice? Great. All right, let's go ahead and do the dice example. Okay, so the dice example says you have a light up little dice, and it wants to be able to represent any number between 1 and 6, because that's what D6 do, right? 6-sided dice. D6, we can represent 6, and it gave you pictures, I think, of all possible combinations. And then it said this is A, this is B, this is C, or something like that. I don't know if that's them, it doesn't really matter. And then ask the questions of this. That is fine. Yeah. Right. Because there are situations, it's optimized where like this light and this light are always on. There's never a situation. So this is also A and this is also C, basically. But we don't need to know that yet in order to understand the design. And so the question becomes, if I'm given an input, how do I make sure the outputs light up? Well, each light is one output, because I can't design a circuit that controls more than one output. So I have to worry about A, B, C, and D separately. So I draw a table that has how many? Well, I need to represent 6 different numbers. So then I go, well, 2 to the 1's not enough. 2 bits, 1 bit is not enough. 2 bits is 4. I can't represent that. 2 to the 3 is 8. Okay, now I have enough bits to represent 6 different inputs. All right, so then I say 3 bits. I'm not going to call them A, B, and C because that's problematic, right? Because my outputs are A, B, and C. I'm going to call them X, Y, and Z. And then I just do 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. There we go. And I say this is 0, 1, 2, 3, 4, 5, 6, 7. How do I roll a 0 on a dice? I can't. Situations that can't happen, we don't care. How do I roll a 7? I can't. Don't care. Turns out, maybe I want to think about this a little while. Like maybe it's actually better to treat other ways and do like this conversion, but let's just stick to the easiest, most straightforward path. No reason to complicate it unless I tell you to, right? And now we go, well, when does A turn on? And when does B turn on? Okay, well, A, if I roll A1, that light turns on, no. If I roll a 2, yes. 1, no, 2, yes. 3 is those 3, so yes. 4 is those, so yes. 5 is yes. And 6 is yes. Well, my K-map is going to be awesome, right? Because I'm going to have a 1, 0 in that. This is going to simplify great. Make sense? Well, I do the same for B. B is this dice. 1. Oh, sorry. We still get a carry, don't care, right? Because B is not going to change in these. So in fact, don't cares are going to carry through all of my A, B, C, D. And then I just say B. 1, no, 2, no, 3, no, 4, no, 5, no, 6. Okay, there we go. 6 got a. All right, that's going to be honest, no K-map 2. And then I just keep going. And then I do the K-maps, which do we need to do the K-map? Okay.
I didn't.
Okay. I don't remember the problem, the exact question, but we could, right? We could ask the question. Now let's solve the K-map. Well, this one is A. It's not A and B. I would have to draw a second there. And then I'm just going to do this direction X 0, 1, 1, 1, 1. Don't
The B1, right?
yeah,
And the
1,
BX.
don't care. And then I have to figure out how do I solve this K-map? Well, it's really just going to be 2 circles of 4. Or I could do the product of sum. That's that. That's also totally viable if I don't specify otherwise. And then I would go and I would write B. I would do a new K-map. And I would solve for B. Then I would have 2 different circuits, each of one controlling 1 light. So that's all in this class. All of your problems, at least for the first half or so, are going to start from this question, which is I'm going to ask you to design a circuit that does something. You're going to draw a truth table. You're going to turn the truth table into a K-map. You're going to turn the K-map into a circuit. You're going to turn the circuit into an AND and OR gate. And then you're a digital designer. And then we'll learn HDLs and we'll kind of optimize the process. You're welcome.
I'm sorry, I'm still a little bit confusing truth table.